Hello, everyone. Let's keep talking a bit. I am looking generally to talk to you today about a couple topics. One of the topics is the kinetic theory of gases, and from there we can, we'll proceed. We'll take a look at see some of what the book says, some of what I have copied from some of the books, and we'll kind of take it from there. So we're talking about kinetic theory of gases, guys, for this part of the discussion. And let's see some of what they say. I mean, the Survey and Buell book for Physics 120, Volume 1, Edition 11, covers this material really well. If anybody is looking at this video and they're not in Physics 120 and they're in Physics 209, this works as well. It works for the Physics 209 material as well. So how I'll probably label this is the kinetic theory of gases, and we'll take it from there, I guess, when I do it. So it'll be accessible to both parties, to the people Physics 209, the calc treatment of Physics 209, and the non-calc treatment of material, which would be the Physics 120, both in regard to mechanics, you guys. So for those who have access to the Survey book, Volume 1, Edition 11, on pages 137 through 139, they say some pretty fascinating stuff. And then they go into some different, then they go a little bit further. So from 137, let me have a look at it here really quickly, guys. Pages 137 through 143 in a sense, but maybe not quite all of that, but they give some good examples that way. Those of you in the calc version of mechanics, Physics 209, you may not have access to that book, but you can find that in other books. You should find it in the notes here. For the non-calc version, as we said, the 120 of mechanics, non-calc version, we have the Survey book, Volume 1, Edition 11. Well, the kinetic theory of gases, what are they talking about? They say a couple things here. Let me kind of read it out verbatim, I guess you could say, and then figure out exactly how I want to go with this. All of this is in my notes. Whether you're in Physics 209 or whether you're in Physics 209 or whether you're in Physics 120, even in some other physics classes I have it, but for sure in 120 and 209, I do have all of this on Canvas. Everything is backed up, you guys, on Canvas, so don't worry about that at all. So with this in mind, let me say a couple things and kind of get the ball rolling with it, I guess you could say. Let me read it verbatim out of the Survey book and kind of take it from there. For the kinetic theory of gases, using the model of an ideal gas to describe the kinetic theory of gases. With this theory, we can interpret the pressure and temperature of an ideal gas in terms of microscopic variables. The kinetic theory of gases model makes the following assumptions, and then they go ahead and they give us 5 different assumptions here, I guess you could say. Assumptions of the kinetic theory of an ideal gas. Number 1, the number of molecules in the gas is large. In fact, you can assume it's very large. I'm telling you that as well. The number of molecules in the gas is large, and the average separation between them is large compared with their dimensions. Because the number of molecules is large, we can analyze their behavior statistically. The large separation between molecules means that the molecules occupy a negligible volume in the container. This assumption is consistent with the ideal gas model in which we imagine the molecules to be point-like. 2, the molecules obey Newton's laws of motion, but as a whole, they move randomly. Okay? So the molecules definitely obey Newton's laws of motion, and we're going to exploit that reality. But as a whole, ladies and gentlemen, they move randomly. By randomly, we mean that any molecule can move in any direction with equal probability with an equal distribution, with a wide distribution of speeds. Okay? We'll talk more on that and what assumptions we can make. Number 3, the molecules interact only through short-range forces during elastic collisions, perfectly elastic collisions, with the walls of the containers and with themselves when it does happen, if it were to happen. We're almost assuming that it doesn't happen because there's so great separation between them and they're point-like particles. Definitely, though, all collisions will be elastic. This assumption is consistent with the ideal gas model in which the molecules exert no long-range forces on each other. That was 3. 4, the molecules make elastic collisions with the walls. Okay, I kind of already said that. I jumped the gun on that one. 5, all molecules in the gas are identical. Okay. If they're not, we got to treat them like they're a number of different gases. Each one of the individual gases themselves have identical molecules, and we'd have to say, there's a lot we'd have to say at that point. But for our purposes right now, all molecules in the gas are identical. Although we often picture an ideal gas as consisting of single atoms, molecular gases exhibit, okay, this is the big thing that kind of lets us off the hook in a lot of ways, you guys. Although we often picture an ideal gas as consisting of single atoms, molecular gases exhibit ideal behavior at low pressures. On average, effects associated with molecular structure have no effect on the motions considered. So we can apply the results of the following development to both molecular gases and monatomic gases. This is very important. And you see, and sometimes the way it gets written in some textbooks, for my memory, I'm only one on memory here, it gets a little confusing what you're allowed to assume, what you're not. But for our purposes here, this is very important. Although we often picture an ideal gas as consisting of single atoms, molecular gases exhibit ideal behavior at low pressures. On average, the effects associated with molecular structure have no effect on the motions considered. So we can apply the results of the following development to both molecular gases and monatomic gases. Forgive me for repeating that, guys, but it bears repeating. It doesn't matter the molecular structure of the gases. As long as the right conditions are in play that allow you to have consideration that there's an ideal gas. As long as it can possibly behave as an ideal gas, the molecular structure doesn't matter. It could be monatomic, or it could be a polyatomic. It could be a monatomic molecule, a single atom, or it could be rather than just monatomic. It could be monatomic, or it could be polyatomic and still behave like an ideal gas in the right conditions. So they talk about a number of things here, guys. Let me try to develop an argument. Let me not go necessarily verbatim or relatively close verbatim to what the book is saying, but let me say some other stuff. We're going to look at some stuff and from there draw some conclusions. There's a lot can be said here, and I think it's something that we need to look at. So, and then we'll kind of hook around and draw some conclusions with it. I'll already tell you some of the conclusions, and then we'll kind of prove much of what's going on. And there's things that they can, I guess you could say they're things that can be visualized at the macroscopic level. I mean, I can visualize pressure at the macroscopic level because I know there's a force being exerted on an area, and I can measure that. I can also measure a volume. I can also measure, I may not be able to measure the number of molecules, but let's come back to that. Maybe we can. There's an ideal gas constant, R, and there's absolute value temperature. And so they talk a little bit about that. And you can actually find out the number of molecules if you are aware, if you have a measuring stick for that. If you say, I don't know, there's 1 gram of something, there's 12 grams of carbon, which has an atomic weight of 12, and then from there I can kind of, there are ways they have proven to find out how many molecules would be necessary to get the 12 grams of carbon, to get 1 gram of helium, to get 2 grams of hydrogen. How many molecules would you need? That's Avogadro's number, 6.02 times 10 to the 23rd particles per mole. There's a lot you can say here. Let me actually right now kind of look at where it's going to go with that, what they're saying. Trying to say a few things regarding this. Just make sure it's fine. We'll see how we can look at this and how some of these conclusions can be drawn. Just trying to find where they would have said something here. Okay, let me say a couple things that we will use, and then we'll kind of get a gut idea of what's going on with the kinetic theory of gases. We're not going to worry too much about specifics. We're going to say the circumstances are such that we can do a lot of stuff and know a lot of stuff. Well, with that in mind, let's see what I can say here. Let me see if I can write a few things and kind of take it from there. put the carriage in front of the horse. Well, let's say a couple things that we should know, we will know, and I'll leave these up here, and periodically we'll come over here again. They got this number, capital N sub A, called the Avogadro's number, and it's roughly equal to 6.02 times 10 to the 23rd particles meaning monatomic atoms or polyatomic molecules. I'm not counting the particles that are within the molecule. I'm counting every single molecule that may have 10 atoms in it. I'm counting every one of those as one particle. So leave this, put this up here. So you got particles per mole. 1 mole, so basically what this is Avogadro's number. This means the number of molecules in 1 mole. 1 mole, a little extra here, I guess. 1 mole is 6.02 times 10 to the 23rd molecules / atoms. Or atoms, So molecules, atoms, I don't want to say too much on that, guys. Maybe make it a little more confusing than it's helpful. The mass of a single atom. For that purpose, I guess you could say even the mass of a single molecule, if you play it right. If you know the molar mass, in other words, kilograms per mole. So if you have the molar mass, molar mass, you guys, would be, trying to think here now how exactly to find one of them. If I knew that 1 mole of, I don't have periodic table of elements in front of me, so I'll use something for which I know, I guess you could say. If I knew that the mass of 1 carbon atom was 12 grams per mole, that means 12 grams for a group of 6.02 times 10 to the 23rd particles, atoms. 6.02 times 10 to the 23rd atoms is 12 grams. If I divide by 6.02 times 10 to the 23rd, I'll know how many grams 1 molecule, or 1 atom in this case, of carbon is. So they say the molar mass divided by Na, Avogadro's number, 6.02 times 10 to the 23rd. So it's that. So much of what goes on, you guys. So much of what goes on uses this thing they call the ideal gas law. And I'll see what I can say to get us there. I've seen different approaches. What I have at my disposal right now immediately, and what I think about our time frame and stuff is going to determine a lot, I guess. But we talk about the ideal gas law, and this thing has huge significance. Gets used quite a bit. If you look at some of my work with some of the processes that go on, when we talked about various processes and their gases present, we talked about the iso. I'm about to erase this again. You already have this in another video, but you talked about the isobaric process. Isothermic process or isothermal process. I think it's isothermal. It's a horse apiece, guys. Isobaric, isothermal, adiabatic. and isovolumetric. Isovolumetric, okay, that's why I'm a math teacher, there's a little physics sometimes, I can't spell. So you're looking at these four, you guys. Iso is a Greek word, a lot of words. I don't even know how much of English is Greek. I mean, there's a huge part of the beautiful English language has a lot from Greek and Latin, a tremendous amount. So a very great amount from Greek and Latin. Iso means equal. Baric has a V sound to it. Vados, baric. Vados means weight. Isobaric means equal weight. There's equal pressure throughout some process that involves a gas. It could involve an expansion of a gas. The gas could still expand, and the gas could still expand within a piston, and could still contract within a piston, and still have an equal volume. So this isn't, I'm sorry, wouldn't have an equal. The volume would change. Volume could change. The gas could expand, or it could contract, but it could still be an equal pressure. Isobaric, isobaros. Isobaric process is a process where the pressure does not change. Isothermal process, iso equal thermal, thermos, is warm. So the temperature doesn't change on something like that. Adiabatic process. Is a negation. A means negation. What am I? My example, the example that they gave me when they were teaching me this was atypical. A means un. Typical, typical, that you usually see written. So, via means through. Vatikos, to go through. Nothing goes through. There is no heat exchange. There is no heat being brought into the system. There's no heat from the outside. There's no heat leaving the system. There's no heat entering the system when we do this. Isovolumetric process is the volume stays the same. And again, that stuff I can tell you from where we can actually find that, it should be. Let me try to just find it, guys. I can also give you a place to look. And they go into this thermal processes. They write them down. They got them. They actually have these. I could have sworn they had these written down somewhere. They did have. They do isothermal, the whole thing. Let me show you. And there's combinations of the above. We'll get to that as well. Isovolumetric. So Q is 0, you know, the temperature that comes through on something. So I'm doing a few things here, guys. Let me just, given the time constraints that we have, let me try to say something of importance. I do have this already written elsewhere, you guys. And there's also, for these processes that I kind of wrote up here for you guys, the book's got great coverage on it. There's general cases when a process follows none of the four given models, it's still possible to use the first law to get information about it. The work can be computed from the area under the curve, and if temperature and endpoints can be found, delta U follows. I'll make a long story short. There may be situations, you guys, where you don't have this. You simply, you don't have any one of these. Hey, it's for sure isobaric. It's for sure isobaric. For sure isothermal. For sure adiabatic. For sure isovolumetric. It's only this, or it's only that, or it's only that, or it's only that. Yeah, that happens a lot. Sometimes you can kind of utilize all these to solve something in a more general case of what they're trying to say there. This I have coverage on in another video, you guys. So you'll see that when I talk a little bit more about that. I only did like 2 problems, but I think like each problem had, I don't know, anywhere from 5 to 10 parts to it. So we're effectively doing anywhere from 10 to 20 problems just in those 2 problems or something. There's a lot in there. So you'll see that in another video that I have. Related to this, but this is some of the stuff they're talking about. The book's it's a great book. Like as I told you guys, it's got a great book. It's a great book on this stuff. When you're talking about these, it's a good place to look for this. Thermal processes, 389. Let's see how far it goes here. And they got some one, you know, this, again, I can't emphasize, this is a great book. From 389 to 396, Thermal Processing Gases. And there's some great, and they got example problems that are just wonderful. They got some wonderful example problems in there for you as well. Again, the book's just a tremendous tool in that regard. We use, to solve these, to use these, there's mathematics that comes into it, and there's stuff I'm going to do. There's stuff I'm going to do with the ideal gas law that's going to make all this stuff make more sense. Let's get to it. I mean, I'm kind of giving you kind of the conclusion of how powerful the ideal gas law is. Let's actually get to how they actually derive it, or at least come close to deriving it, and we'll kind of take it from there. So let's see here, guys. They talk about the change in the internal energy of a system, and that's, again, they go into this in quite decent detail, but on page 386, the first law of thermodynamics. And this first law kind of gets written differently in different books. Not much differently. It's a question of U minus UI, and I'll talk to you about what that means in a second. So, as long as you know U means internal energy. Total internal energy of what's going on, and that's composed of a number of things, you know, but it tells you, it pertains to the motion that's going on. So you can kind of maybe a little more briefly write it like this. Now this gets different, this gets written differently in different books, guys. This is, I just got rid of this. The change in the change in the internal energy of a gas. The change in the internal energy of a gas is equal to the heat exchange plus the work that's done. Now you got to be careful here. If a system undergoes a change from an initial state to a final state, then the change in the internal energy, delta U, is given by delta U equals Q plus W, where Q is the energy exchange between the system and the environment, and W is the work done on the system. Now this is where you got to be careful. The work that's done on the system, if there's a piston and it's full of gas and you're going to compress the piston, you're doing work on the system. You're doing work on that gas that's confined to the piston. You're doing work on it by pushing with a force over a distance. Push with a force over a distance downward to compress the gas. You got to do work to do that. That's the work that you did on the gas. That's a positive number when you do work on the gas. When you press that piston down, you're doing positive work on the gas. The environment, in a sense, me, part of the environment, I'm doing positive work on the gas by pressing that gas down. Doing positive work on the gas, and maybe I'm heating up the gas while I'm doing it. Positive plus positive is a positive change in internal energy. The internal energy is even greater. They regard W as zero if no work is done. Positive when you do work on the gas, when you press on the gas, and you confine the gas somehow, you make its volume smaller, you're doing work on the gas. You're doing work on the gas when you make the volume smaller. You're doing positive work on the gas when you make the volume smaller. If the gas expands, so if you press on the piston and make the volume smaller, you're doing positive work on the gas. But if for some reason, somehow the gas expands and the volume gets bigger and the gas pushes the volume upward, the gas is doing work on the environment. It's doing positive work on the environment, but negative work is being done on the gas. Make a long story short, the environment's doing negative work on the gas because the environment's experiencing the change. So when the gas expands, the gas is doing work, and we call that negative work. We call that negative work when the gas expands. So that's the peculiarity of the definition, at least in this book. It's a great way to define stuff, if you ask me. I think it's the best. I've seen it in other books. This is my opinion. I've seen it in other books where they do something different. They're talking about the exact same theory. It's the exact same reality, and the mathematical beauty of what they're doing is exactly the same. They just have a different way of talking about it. My opinion, for whatever it's worth, this is the best way. This is a very good way to do it. So let's see. So the way we got it is, the way we can look at it, that's the best. That's a good way to do it. So this stuff, this right here, and this right here, found in the book. I've discussed it elsewhere. I've got it in the notes, hard copy for you as well on Canvas. It's going to help us do a lot of the problems we're doing with thermodynamics. Now, I've been saying this. I've been jumping all over the place with this thing. We're talking about the ideal gas law. Is there anything we can say regarding something like this? Well, I've seen different things said. Let me see what I can tell you that I think you're going to believe and that I think you're going to like. As we looked at this, give me 1 second here, guys. And there's so much else here, guys, and it's in the notes, and I'll try to have it there. I guess what can I say? I might maybe right now be a good time to actually bring some of this stuff to the forefront, I guess, when we do this. And yeah, I'll write some other stuff. At least maybe summarize what you got to kind of be looking at anyway, I think. So when we're kind of looking at it. So let me see some stuff here that we can say. I mean, we got to this point, and we got, like I said, it's the ideal gas law. But since we've come this far in this process, there's some great stuff we can say here. To what extent we're going to say it, guys? Let me kind of take it with the flow of where I think I can take this discussion, I guess you could say. Let's see here, guys. Let me see. Where did I put that now? There it is. I haven't found my pages here, guys. 332, okay, way back there. So again, we're going to come back. I didn't lie to you about this ideal gas law thing. It's pretty important. We're going to see it. Okay. So, all right. There is some other stuff here, and I guess when you find it, there's like I have something I talk about, and like I said, I've got it written out for you on Canvas, the kinetic theory of gases. So there's a couple little packets that you want to look at on Canvas if we get our signals crossed, guys, and with all the understandable chaos that is nobody's fault that happens. I really want to be seeing you guys a lot more. Hopefully things straighten out, but what do we got here? We got, there's one packet. And it should be labeled like this in Canvas or very close to it. So when you click on it, you'll see what I have written out there for you. Now, do I ask you to derive these things? No, I don't really ask you to derive any of the derivations that I have. I have a lot of them there for you for your personal enrichment. How much time do you have? Well, I know you're going to be working really hard doing a lot of things, not just my class. It's there for you if you want it. Okay, it's there for you if you want it. So you got this, the kinetic theory of gases. Got another one labeled, fluids, thermal properties of matter, oscillations and waves. And this is for both, and this is for calc-based courses and non-calc-based courses that I have here. Fluids, thermal properties of matter. Oscillations. A little bit of a summary, I guess you could say. And the other one's a couple other stuff here, guys. And again, you don't need to know derivations here, guys, on a lot of the stuff that I'm doing, but it's good to have the, again, for what level you want to have some of these things that we're doing. Down the road, we're going to be doing oscillations a little bit. So we got this. The other one, trigonometry and waves. Those of you who have the calc background, you might like this. Again, I'm not going to ask you to derive this stuff. You do have to know how to use it, though. You got to know. I mean, if the problem's given to you, you got to know somebody somewhere, before my teacher, of course, and somebody somewhere well before my teacher derived this stuff. You want to know a lot of how this stuff looks? Go ahead. Please read this stuff. You don't have to, but you got to know how to derive it. Okay, and we're doing this. So I don't know. This is not written in the best way, but I think you guys can read it. So those 4 items are pretty useful. And there's some stuff on there, and I can, you know, I came this far with the stuff. I'll maybe say a few things on it. I'll maybe hit oscillations. Maybe the next video today, when I briefly do it, I'll probably get into oscillations a little bit. We'll see. It might not take too long on that. Since we got this far, let's keep working this thing like this. I'll leave this, I'm gonna leave this up here. You guys can always come back to it. I always forget that nobody's in front of me, right? You guys can always just rewind and see the stuff I wrote, so you're gonna be fine. You can always rewind on that, guys. And there was other stuff. You see the stuff I did earlier, the last time we were together when we talked about Bernoulli's equation, when I talked about fluids. I talked about fluids, Bernoulli's equation. You saw me do that. That's also on Canvas. It's all on Canvas, guys. I got more stuff on there than I have time to look at. I'm the guy who wrote it over a number of years. You know, it's just, you're not going to read all of it, but there's stuff on there. There's stuff on the Doppler effect as well. We talked about that some other time. You know, at what point do you talk about this stuff? I mean, sooner or later you talk about it. Maybe bring up the Doppler effect at another juncture. But earlier we had, you know, this stuff kind of goes with it. We had. You know, and one of them we had, since we're here, guys, might as well. I got enough stuff up here. Let's look at it some more. We got fluids. Bernoulli's equation. I have it in capital letters. I'm writing in small letters here. Yeah, he's some amazing, really amazing mathematicians, guys. Back in the day, before the supercomputers, before all that stuff, they old school knew a lot. I have a derivation elsewhere. Of the Doppler effect. So there's another 2 for you, I guess. One, 2, 3, 4, 5, 6, and there's a whole lot more. I got other stuff where I'm actually trying to, remember when we were talking about moments of inertia and torque and angular acceleration and stuff like that? I have some proofs for you as to how to talk about how to prove moment of inertia, how to prove the parallel axis theorem associated with moment of inertia. I've got a proof of the parallel axis theorem. I looked at something out of a book. They gave a great proof of this. I also looked at something, I also tried to look at it my way, and I'm sure I wasn't the first guy to do it. I'm sure that this was done by other people, but I tried to look at it just kind of individually to look at another way to do it. So I've got something that I kind of threw together. I'm sure other people did it long before I did. I got what I tried to do, as I just said, and I had from another book, some proof related to moments of inertia, things like that. There's a lot of stuff there, guys. There's more than we can cover in the circumstances that we're in. That's nobody's fault, but it's all there. It's all on canvas, so the coverage is there for you. The problems, you got hundreds of problems at your disposal, many hundreds of problems at your disposal. If you're working this the way you should be working it, you should be in pretty good shape. You should be in really good shape, okay? And I know that you will be working this hard. So here we go. We got all this stuff right here. Being that we're in the thermodynamic aspect of things here, right, guys, before I jump to this kinetic theory of gases, I know you almost forgot what I was initially going to talk about, right? We got this, so since we got to here, because this thing right here really is like maybe it's good that we do it after the fact. It's kind of the granddaddy of all of them, in a sense. You can kind of argue a whole bunch of what's going on. This kinetic theory of gases really explains everything there. So let me throw this stuff at you at the macroscopic level, and then let's go microscopic a little bit and see what we can say. All right, so we said a few things here, guys. So let's keep talking, I guess you could say. We are, let me see here. Okay, look, we got this. Let me see. There is, they show a bunch of stuff. Let me kind of pick and choose on this one. They talk about mechanisms of heat transfer. I think at some point I got to talk about it. And if I didn't, and we run out of time in our process, we've done a lot, but there's always more. That's kind of the beautiful thing about physics. But let's talk about a few things, guys, regarding some of this stuff. Again, we said that. Where were we? Where did we? Did I write it anywhere? I did not just yet. Okay, when we talk about this kinetic theory of gases, you guys, we will have this very much in the back of our mind. It's this thing is so useful. I swore I wrote it down, guys. Apparently I didn't. Okay. PV equals nRT. What are the units? I can almost tell you who cares, as long as you're consistent with the units always. Yeah, let me qualify that. We really care when it's about temperature. There has to be an absolute temperature scale. How many of those are there? You could probably make up as many as you want to make up, but they all have to have one feature in particular. If there is no molecular motion taking place, then there is no pressure. The more molecular motion that is taking place, the more the pressure. It's about as simple as that. There's more to it. Devil's always in the detail, you guys, but for right now, let's put it this way. If the molecules aren't moving, they're not exerting pressure. That's temperature zero. They call that absolute zero. If the molecules are moving fast, their molecules will collide violently against the walls of the container, and they will push against the walls of the container in aggregate. And that's pretty significant. When they push against the walls of the container like that, there's going to be a lot of pressure. What if you doubled? Well, let's time out. If the average kinetic energy of the molecules that are present is a particular amount, let's call it amount KE. If you were to double the average kinetic energy of those molecules, each one of them, on average, if you were to double them, and they went from KE to 2 times KE, there'd be twice as much kinetic energy. Twice as much kinetic energy associated with each individual particle on average. And that would affect the pressure. That would make the pressure greater. By how much would it make the pressure greater? If you doubled the average kinetic energy, you're doubling the absolute value temperature, the pressure would double as well. Pressure and temperature are related to one another the way straight lines behave. There is a linear relationship between pressure and temperature. If you triple the absolute value temperature, you are tripling the pressure. If you make the absolute value temperature 1/3 of what it was, you're making the pressure 1/3 of what it was. All other things equal. assuming you kept the volume unchanged, assuming you kept the volume unchanged, assuming you kept the number of moles unchanged, or molecules. Well, molecules is a different story. You gotta do some other stuff to it to make it molecules. But basically, this is number of molecules. They say it in moles because it's just easier to do bookkeeping. I don't want to be writing 29 times 10 to the 25th. You know, it's just easier if I write it in moles. You know, so and R is a constant. So this is huge, and we're going to come to this. We're going to look at it. We're going to explore it. We're going to figure out what's going on, and I think we're going to be in pretty good shape when we do so. Okay. With that in mind, I mean, since we got to where we got, let's just say a couple things. There's more here. Again, I'm sounding like a broken record on this whole process. More here than I can say in person or even on film. But let me give you something, at least that, I mean, we've done a good amount of this stuff. All the problems you got, you guys, that we're going to look at, man, they're going to hit all the theory as well. If you're studying the book, if you're reading the book and you're reading how I solve these problems, I know you're going to be fine. I know that you're going to be fine. You're going to be in strong shape. Nothing's guaranteed. Again, it's up to you how things proceed. But there's I thought there's something here that kind of needed to be said. Even got the Doppler effect in this one. So there's a little bit of repeat on some of the stuff that we have in here. They've got these three mechanisms of heat transfer that you want to talk about. I just wanted to kind of bring it up to you guys, so at least we have it. So let's see exactly how I'm going to say it. Like some of this I'm going to erase. Maybe all of it gets erased eventually. I'm going to probably try to keep what I got as you guys are looking at me on this far side over here. I'm going to try to keep all of it up there. But if I don't, like I said, you've got the feature where you can just go back and look at what I wrote there. So you got some mechanisms of heat transfer. Mechanisms of heat transfer, and they give us three of them, guys. I just figured you might want to know this. I'll say a couple things here on this. I think we need it. So perhaps me calling this this video the ideal gas law. Maybe I need a broader definition of it. Some thermodynamics or something, right? Thermal processes, you know. So we'll call it that. But the ideal gas law covers a lot of stuff. But I think when I do label this, I guess you'll see it, guys, under the heading. I would probably say thermal processes, something like that. We'll talk about it. So regarding some of these thermal processes, let's talk about how heat gets transferred. And they give you three things here. They say conduction, convection, and radiation. What's going on here? Well, there's three ways that we know of in which heat is transferred. Conduction means if you have, just kind of block this off this way. Conduction, you guys, let's say you had something here, and you had some metal here or something like that, and or something, you have something here, and there was a temperature here. There's a temperature differential between the two places, and let's say there's a rod, there's a steel rod here or a metal rod here. It is let's say it's circular, it can have all shapes and sizes. It can be a rod of small diameter, large diameter. The distance between the two places where the conduction is taking place. So this could be, let's say this is temperature, there's heat, there's average temperature here is hot, average temperature here is cold. The distance, the difference between the two, delta T is TH minus TC. This distance right here, we'll say it's capital L. The cross-sectional area, and we're saying this is uniform, so it's this cross-sectional area right here in the middle is the same as the cross-sectional area right here. That cross-sectional area is A. There's a constant K, and what's going on here, guys? So let's see what we have here. So these mechanisms of heat transfer. I just think it's important to know, guys, you're never, even in the best of circumstances, and certainly what the crisis the world is kind of facing right now is certainly not the best of circumstances. Even in the best of circumstances, no teacher's going to tell you, can tell you every single thing verbatim in a lecture format. They can point to all of what you got to do, and I'll try to do that as well, as best we can on this thing. But for the mechanisms of heat transfer, what's going on? And this is found in various chapters, guys, so I'm kind of going all over the place. So we'll call this like thermal processes, is probably a good thing that I'm going to call it. So I'm not even associated with any particular course, because I think the 120 and the 209 can equally use this. So you guys should be in pretty good shape here. What's going on? There's a place here, there's a reservoir here that's hot. There's a reservoir here that is very hot. There's a reservoir here that is very cold, or so to speak. There's a reservoir here that is cold. There's a reservoir here that is hot. There's a rod here, and the only way conduction is going to take place is through that rod. I will tell you something. Heat, called Q, I know I've used Q in different context, in using it meaning different things in the past that you've seen. But here, Q is going to be heat. Q is the amount of heat transferred per unit time. Now, I don't know if you guys remember, we know, let me not write too much here, guys. Let me just kind of tell it to you. We know that work divided by time is power. The amount of heat transferred per unit time is the rate at which heat is being transferred. You can also call that power. The rate at which heat is being transferred, you can also call that power. Always, heat flows when there's conduction going on. When there's conduction going on, the aggregate amount of heat that flows always flows from the hot reservoir to the cold reservoir. Heat always flows from hot to cold. So it's going to go this way. What is the rate at which it's going to go? Here's where I'm asking everybody to kind of use their gut feeling for what they think could be going on here. Q is the amount of heat in joules. Delta T is per unit period of time. That's energy divided by time. That's power. The rate at which heat is transferred, is dependent upon, well, there's a constant called K that makes things work out for us. It's directly proportional to the area, the cross-sectional area, inversely proportional to L, and directly proportional to shot something else, man. I start out with a full stick and I got nothing. I of course don't know how to write anything, but all right, so let's keep going, man. Luckily I got like 3 boxes, so I think I'm set. All right, guys, what's going on with this? What's going on? I think our common sense will lead us to where we gotta go. The rate at which heat is transferred, the energy transferred in the form of heat per unit period of time, the rate at which heat is transferred, is directly proportional to the cross-sectional area. What does that mean? That means if there's a big amount of cross-sectional area in contact with the reservoir, if there's a big amount of cross-sectional area in contact with the reservoir, there's more opportunity for heat to flow. So it makes sense, you guys. K is a constant. That's the same constant for everybody, big or small. Whatever the constant is, it is, and it's a constant for everybody. If A is big and everything else is the same, there's more flow of heat. There's greater rate of flow of heat if A is big. Is that believable? Sure it is. If there's a lot of contact with that heat reservoir and it's extending all the way across so you can hit the other heat reservoir that doesn't have as much temperature, the temperature that is here is small. The temperature that is here is big. Low temperature reservoir, high temperature reservoir. It's going to go from high temperature reservoir to low temperature reservoir. The flow of heat, we already said that. Here it is. Q's going to flow that way. And if A is big, there's more opportunity for the flow of heat. So it's directly proportional to A. It's true. Inversely proportional to L, what does that mean? Well, if L is short, it's more conducive to the flow of heat if L is short. If L is short, it's going to have an easier time getting there. There's less resistance to the flow of heat if L is small. If L is small, there's less resistance to the flow of heat. So if L is small, we all know this, guys. If the denominator is a small number, it makes everything big. So if L is small, yeah, that's going to give me a big heat transfer. So I got to put it on the bottom. Small L will give me a big answer. Big L means there's a lot of resistance to the flow of heat. There ain't going to be as much flow of heat if L is big. So you got to keep them on the bottom. So it's inversely proportional. The rate of flow of heat is inversely proportional to the length of the rod, inversely proportional to the length of the rod, directly proportional to the cross-sectional area of the rod, and also directly proportional to the temperature difference. If things are close to the same temperature, you guys, there's not much flow of heat between them. Why would there be? They're close to the same temperature already. We already know that. It's hard, it's hard for that to happen. I mean, the water you have, the ice water you have goes to room temperature. Well, the room's got a temperature, the water did have a temperature. Well, that's some other stuff going on here as well, guys. I don't want to be too much on that, but you can see that generally, if there is a big difference here, there is a lot of potential. Delta T means a lot of potential for the flow of heat. And that's where they're coming from. When you do this. In all of these temperatures, you guys, that we were talking about, they've got the absolute, you can't, I think I've already, sure I did. I'm remembering this now, and I'm sure you'll see it again in one of my videos, but I'll say it again. We're talking about the temperatures here. What are the temperatures under consideration? Well, you got a delta T here, so there's some leeway here, but usually you want things in the MKS system of units. Kelvin temperature scale is identical. Each step, each gradation in the Kelvin temperature scale is the same as 1 degree Celsius. The difference is that negative 273.15 degrees Celsius is absolute zero. For the Kelvin temperature scale, they just call it zero. You've got to have an absolute zero, and that's the Kelvin temperature scale. One gradation, this is just gradation. 1 Kelvin difference. A delta T of 1 Kelvin. Maybe I should say this a little differently. A delta T of 1 Kelvin equals a temperature difference of 1 degree Celsius. Absolute. Again, the Kelvin's at 0. If you want Kelvins, you take Celsius and you add 273.15, or just 273, for our purposes. This ideal gas law that I wrote earlier, you guys, only works when you have an absolute value temperature scale. When you have an absolute zero, rather. When you have an absolute zero temperature scale, it's the only way this mathematics is valid. I can't say, as I've said in the past, I cannot say this, as I've already explained to you in the past that we cannot say this. I can't say it's 100 degrees today, and it's 100 degrees Fahrenheit today, and it was 50 degrees Fahrenheit yesterday. Therefore, 100 degrees Fahrenheit divided by 50 degrees Fahrenheit is a ratio of 2 to 1. That means it's twice as hot today as it was yesterday. That means if I'm putting it into this equation, it's going to be twice as much pressure. No, 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 no. It's not twice. The average kinetic energy of the molecules is not twice as much. I have to be on a Kelvin, I have to be on an absolute value, an absolute zero temperature scale to do that. If I were to say to you the temperature of this gas is 300 Kelvin, the temperature of, right now it is, an hour from now, we're gonna, in the experiment, we're gonna bring it to 600 degrees Kelvin. 600 degrees Kelvin divided by 300 degrees Kelvin is a ratio of 2 to 1. For sure, the average kinetic energy of the 600 Kelvin circumstance where the gas finds itself, the average kinetic energy of the gas at 600 Kelvin is twice as much kinetic energy on average as that same gas at 300 degrees Kelvin. 600 Kelvin divided by 300 Kelvin is a ratio of 2 to 1, and the ratio of the kinetic energies in those circumstances is also 2 to 1. That is very important. That's true. That's true. So we already kind of, I've said this in different circumstances. The book goes into it. Forgive me for hooking around again, guys, and talk about it, but I think it's something that needed to be said. All right, so we're there. So this is fascinating. Actually, the way things flow here almost has an analogy of later on what you're going to see in electricity and magnetism when we talk about the flow of current. How much current flows per unit period, how much charge flows past a cross-sectional area per unit time. How much charge flows per unit time. What makes this a large flow? Well, there's not a lot of resistance, and there's a lot of pressure called voltage. Well, this guy acts a lot like voltage in a sense. Now we'll cross these bridges as we need to, but right here, this is the scenario of conduction. Things are conducting. The molecules are bouncing off each other. Bam, 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 bam. The atoms are bouncing off each other to the point where, at the end, all that vibrational motion, oscillatory motion that takes place, all that oscillatory motion taking place, bam, is hitting here and is transferring heat to this guy. It's transferring heat over there. They got a thing called, that's conduction. That's conduction. Convection is when a whole body of particles moves from one place to the other and they change the temperature that way. Perfect example, there's a cold front in Canada that's going to come down. There's a cold front in Siberia that has found itself here or somewhere else in Europe. Pole masses of air mass, cold, is coming to a place where it was warmer, and that's changing the temperature. Water flow. Cold water is flowing to a place where there's warm water, or warm water to a place where there's cold water. That's convection. That's a macroscopic physical flow of material, different from conduction. Radiation. There's a number of ways this stuff gets written, you guys. Q over delta T equals E is a constant. It's not Euler's number. It's not that beautiful number, 2.17, 2.7, 1828, none of that. It's not that. It's just the emissivity constant. Sigma is Stefan Boltzmann's constant. There's two constants right here. A is the cross-sectional area exposed. And T is the absolute value temperature. You can't use anything other than the absolute value temperature for what they got going on here. Or if you're going to use another kind of absolute value temperature that you, let's say, invented, you got to do it consistently, but there's got to be an absolute value there. Okay, I don't want to we're not opening that can of worms. Right? We got the absolute value temperature that we need. It works just great for us. You're not going to use anything other than an absolute value type of temperature, than an absolute zero type of temperature. And there's a number of them. You can bet any you wanted, I guess you could say. The mathematics will work, and you have to do a whole lot of other stuff. We've got the Kelvin scale, and that's an absolute zero type of temperature. What's going on here? For radiation, everything emits electromagnetic radiation at the speed of light. Everything emits electromagnetic heat radiation at the speed of light. Everything. Hot or cold, big or small, no matter where it is. How much does it emit? Well, there's a lot here. I can't give you always the devil's in the detail, you guys, just the way it is. But when we look at something like this, for radiation, once again, we're talking about the flow of heat per unit period of time. E is the emissivity. Something that, E is a number between 0 and 1. 0 means it does not absorb anything, it does not emit anything. 1 means it's a perfect emitter and a perfect absorber. Between 0 and 1. So anything that perfectly emits also perfectly absorbs. It's almost counterintuitive. They call it black body radiation. And basically what it means is it'll absorb everything coming at it and also emit back out. It emits perfectly and it absorbs. Sigma is a constant. This is the low-case Greek letter sigma. A is the surface area of the object under consideration. The surface area that is exposed to the environment, I guess you can say, or at least has exposure to the environment. The more area there is, the more electromagnetic radiation. That makes sense to me. The more area something has, the more surface area it has, the more it's going to be emitting. The more it's going to emit, electromagnetic radiation, or the more it's going to be out there. The hotter it is, the more it's going to be emitting as well, to the 4th power. So that's this. The book's got good coverage of it. Look at that as well. I've got problems that I've done with this. You know the story. You've heard the story. You know how to do it. Okay. So, it's a good amount here, guys. It's a good amount here. It's all there for you. Like I said, I'm probably going to leave a lot of the stuff on your far left-hand side. That way, I'm probably going to leave that board up there. We'll see though. If we need it, I'll be erasing it. You guys, again, I always forget. You guys got the film, so it's not going to be an issue. So we're going to be okay. All right. If we're okay with this, let's get back to the kinetic theory of gases. I mean, it's kind of it's kind of a fundamental thing, but at least the other stuff all of this fits under the category, you guys. Everything I've discussed and will discuss fits under the category of thermal physics. Some thermal physics that we're talking about, okay? So let's see what we can say here, guys. I'm going to say, I'm debating with myself what to erase, what not to erase. Let's just start right here. I'll kind of take it from there. One second here, guys. Don't erase as good as they did last time, do they? I mean, what's going on here? Leave them old, I guess. Well, I'll try to erase a bunch of stuff. We'll figure it out. leaving that there, leaving a bunch of stuff there. We'll see how long I'm going to be doing that like that, but let's see. All right, they talk about, you know, how can we kind of look at this thing and get some kind of sense. Let's have a look here, really quick here. Okay, there's some stuff that they do here. They do it in an order that's rather interesting. I mean, it's fine. It's all there. It's great coverage. I'm the last guy who should be talking about the order I'm doing stuff here, guys. I'm kind of all over the place. But you know, so I might be coming back a little bit of what they're doing here, because I think there was something here that really bears mentioning. I'd like to maybe tie that up here. I think I've done that with my notes. If I didn't, I'll do it on the fly, and I'll try to make it work myself. But I think I have that in my notes as well. So hey, we got to be able to talk. We got to be able to see some of what's happening here regarding this stuff. So let me see how we actually did it. So what I did was on this, guys, I said the ideal gas law. I said it's really important. You know it's important when it occurs in just so many places here, you guys. So they say a bunch of stuff. Now the way they did it, let me kind of follow it the way I did in my notes, and maybe have faith that this is going to work out okay. We've got the kinetic theory of gases. This plays a real central role in a lot that goes on. Just trying to think here for a second. Okay. Let me stay with that. Let me kind of let me erase and go over here a little bit again. So you guys got it. You have it in the notes. You can always go back. So let me say a few things here. I'll leave a couple things up here. I'll leave that up there. The book's got an interesting look at it. I got a feeling I'm going to have to look at my notes a little bit while I'm doing this, guys. I got a bunch of stuff I want to tell you, but we're not going to lose a whole lot of sleep on it. I think we're going to have a strong foundation once we get to where we got to go. Okay. They say a lot of stuff, and I'm going to hook it around and try to make sense why they're saying it. Why we know it. You guys have many of you have already seen this in chemistry, either in high school or at the university level. You may have already seen some of this stuff. There is a constant, and we're not going to really derive a constant. The constants are kind of one of those things set in stone that we just know are true. We can derive it through experiment, if we play our cards right. There's no derivation of it, I guess you could say, but let's talk about it. I gotta talk to you. The number of moles, N moles, is the number of molecules divided by the number of molecules in Avogadro's number. Every time you have, 1 mole, a better way to have written this, I guess, maybe it's good that it's there. This is Avogadro's number. 1 mole, that is Avogadro's number. One mole is Na. That's 1 mole. That's 6.02 times 10 to the 23rd molecules. If I got 18.06 If I got 18.06 times 10 to the 23rd molecules divided by 6.02 times 10 to the 23rd molecules, I have 18.06 times 10 to the 23rd divided by 6.02 times 10 to the 23rd is 3. That's 3 moles. Every time you have 6.02 times 10 to the 23rd, you have a mole. If I got a raw number of molecules or atoms present, that raw number of molecules or atoms divided by Avogadro's number will tell you how many moles are present. It's as simple as that. And there's a lot that gets said, and they kind of hook around. I'll try to make this. I'm trying to hook around and make this thing make some good sense, you guys. See how it goes. Different books have different coverage on this thing. And this will tell you the number of moles. That's the number of moles. Number of moles. Number of moles, huh? How many molecules? Here. Just N. N molecules present divided by Na molecules. That ratio tells you the number of moles. Every time you got 6.02 times 10 to the 23rd, they call it a mole. So let's see what we can do here. They say a lot of stuff here, and so they say a lot of stuff, let me say a lot of stuff, I guess you could say. We've already talked about PV equals nRT earlier. Let me write it down again. And we'll talk more on this one. It's that important. Here we go again. PV equals nRT. PV equals nRT. Is that the same as PV equals nRT, small n is equal to capital N divided by capital NA RT. True. Yeah, they switch it around on you a little bit. They go PV equals, instead of the small n there, they use this guy. They use this right here, that's the n, and they kind of put, they move the big N by itself, and they put R over NA. Well, these guys are both constants. So a constant divided by a constant is another constant. Here's N. They got this thing called, I'll put it right here. KB, this is not Stefan Boltzmann's constant that I had written earlier. This is just called Boltzmann's constant. And this is R over NA. That's KB. That's Boltzmann's constant. So they write it here, KB. NKBT. That is interesting, because we are going to come full circle. We are eventually, as I proceed, we will come full circle. That guy right there, this is Boltzmann's constant. This is 8.31 joules per mole per degree Kelvin divided by Avogadro's number, 6.02 times 10 to the 23rd, it comes out to this. It's not of the greatest importance, the specific number right here, right now, but again, knowing how it's derived is more important at this point, and we can always come back and look this up. But we really got to make a point here. We got this. Okay, guys, I'm sorry, I can't, on a good day, I can't write too well. You put me at the bottom of the board, I'm really going to have a hard time writing. But anyway, okay, so we got this. Again, I got to emphasize, PV equals nRT, and PV equals NKBT. So we're looking at this. Let me see what I can say here. Well, let's see where I'm gonna come to. So this is big. Write it down again. Now we really haven't drawn any. You know, I kind of pulled this formula. I pulled this formula out of a hat in a sense. Certainly, in a wide range of circumstances, this is empirically verified. In a wide range of circumstances, this is certainly empirically verified. So with the empirical, huh? From the Greek word empiria. Empiria means experience. Sounds like experience. Empiria means experience, and experience sounds like experiment. Experiment pertains to experience. Empiria, empirical. It's empirical. Empirical means through experience, through some sort of experimentation, if you will, in the context in which we're speaking. This can all be verified experimentally. So it's believable. Let's make it that way. Let's say it's believable. Now let's draw a connection here. PV equals nRT, certainly believable. Certainly believable. Why is it believable? Because I can do experiments and verify that this is a connection that is frequently to be seen. This is a connection that is frequently to be seen, you guys. Okay? So we got that. It's believable through empirical observation. Through empirical observation, we know this is true in a wide range of circumstances. I tinkered with some numbers here, with some constants here, and then I wrote it a little differently. So there's not anything radically disturbing in the process of looking at this and saying that's the same as this. It's the same PV. Why wouldn't it be the same? How did I write it? N. This is an absolute number of molecules. This is Boltzmann's constant. This talks more at a microscopic, this talks more at a macroscopic level. This talks more at a microscopic level in a sense. And it's the microscopic level that we're going to experience, prove something like this, or very close to it at least, and then kind of know it follows that something like this empirical stuff also follows that it makes sense, that it's true based on stuff we've done here. So these are very important. These are very, very important right here, guys. All right, with that in mind, I said some stuff. Again, you can read this in my notes, the notes I told you to look at. I'm going right off in here, the ideal gas law, or forgive me, the kinetic theory of gases. Ideal gas composed of atoms or molecules all making perfectly elastic collisions, essentially equally against the sides of a container, thereby creating the pressure which is manifested. They're going to do this, they show something. Different books have different coverage on this, as I've said. Some don't have great coverage at all, but it's there. Some have great coverage. I mean, this book's got great coverage. There's other books that got great coverage also, you can say. Let's see what we can say, guys. We said this. I'm not going to say, oh, gee, can you derive this mathematically? Yeah, I can derive this mathematically, but the big thing is, empirically, I can see this is true. I can see that's true in a very broad range of circumstances. All right, well, what they're trying to say here is, guys, if you took a box, and again, the book does it very well, it's all better than I'm going to draw. But basically, we're saying here, guys, that for an ideal gas composed of atoms or molecules all making perfectly elastic collisions, essentially equally against the size of a container, thereby creating the pressure which is manifested. There's a number of looks here, and I'm going to do this showing you a box. Just kind of debating how I'm going to do it. I want to make something really clear, too, in a second. something like this. It's a cube. We say it's a cube. It's a cube, it's a rectangular box. It could be a cube, it could be a rectangular box. It could be a sphere, you guys. It could be a really irregularly shaped volume. A volume of very irregular shape. It doesn't have to be a cube, it doesn't have to be a rectangular box, it doesn't have to be a cylinder, etc., etc. It doesn't have to be a lot of stuff. It can be a cube, it can be a rectangular box, it can be a sphere, it can be a cylinder, or it can be none of those. It can be a real, how do you say, almost randomly shaped object that has volume. Any shape object that has a volume, a continuous volume to it, probably exceptions to every rule, I guess, but I guess for our purpose, if it's continuous and the molecules can freely flow everywhere, shouldn't be an issue. Any volume that's present, no matter how irregularly shaped the object is, there is some beautiful mathematical reasoning that can be done. That's not necessarily really difficult, but it's quite tedious. But there's some really beautiful mathematical reasoning that can be done where we break up that irregularly shaped object, we break it up into columns that are irregularly shaped, like rectangular columns. And we can play games with that aspect, that thinking. We can play games with that thinking. We can play games with that kind of mathematics, doing little columns, columns in the vertical direction, columns in regard to depth, columns going, so I could go, if this is the x and y, if this is the x direction, that I'm doing this with my finger, if this is the x-axis, and this way is the y-axis, and this way is the z-axis, I can deal with any axis I want initially and build columns along that x-axis, or along the y-axis, or along the z-axis. I can take any axis and build columns and play some mathematical games, and I can basically draw the same exact conclusions that I'm about to draw. I need you to remember that. It doesn't have to be a cube. It can be any shaped object that has a volume. For our purposes, any shaped object, no matter how irregular it looks. There's no equation for it because it's so random. The thing is shaped like a rock. It's shaped like the outline of a rock. I can still apply. I can still draw the same exact conclusions if I play the mathematical reasoning correctly. And we can do the mathematical reasoning correctly to show that it'll work for any shaped object, any volume, and any irregularly shaped object. Shaped like a rock. You got it. I can do it. We can do the mathematics. So know that conclusion. So when you see this, don't think, oh yeah, this is the only way it's going to happen. No, it's not. This can happen any way we want to have it happen. If we do the right approximations and do the right reasoning regarding calculus, you guys, and are thinking the beautiful mathematics associated with calculus, we're not going to have any issue whatsoever. All right, well, what they're saying here is, guys, in any volume, no matter how irregularly shaped it is, these conclusions work. Now let's just make it easy. You've heard my speech already. Let's make it easy now. You can assume if there's a total of capital N molecules in this box, heated to a temperature, absolute value temperature, capital T, we will make the assumption, there's a lot of ways you can play this. You can play this with components, and you can play it a lot of ways. Basically, the particles are moving randomly, but every particle has an X component, a Y component, and a Z component. On average, there's as much, it's a tough one to call now. In aggregate, over a period of time, every particle is going to hit along the x-axis as many times as it's going to hit along, the x-axis as many times as it's going to hit along the y-axis as it's going to hit along the z-axis. About, on average, we can almost kind of make this happen and say, about at any given time, 1/3 of the molecules are going along the x-axis, hitting the walls along the x-axis. At that same period of time, so that's 1/3 of the particles, 1/3 of capital M. Another 1/3 of the particles are hitting this way, and another 1/3 of the particles are hitting up and down. So a third this way, a third that way, and a third up and down. So let's see what we got here. As we look at this, let's take a look at the X scenario. The X scenario says, let's take one particle and see it's got a mass m, and let's see what its change in momentum is. There's a particle that's here, and let's say it's hitting back and forth. It's going here, and then it's flying back this way, and then flying back again to hit and doing everything. What's going on here? This guy experiences a change in momentum. Velocity never decreases. On average, the velocity stays the same for each particle. The mass is the same for each particle. It's m. And let's just look at the x component of it. So, there's a lot of ways to go when they do this, you guys. You can look at, and again, I've seen different arguments here. They're not, we'll figure out exactly what they want to say on this. I think we're going to be okay. But you can also say, if you're not doing that, just say exactly here what they're doing here, guys. They're going a little differently. You can, like I said, I've seen it played different ways, guys. You can say at any given instant, 1/3 of the particles are going along the x-axis, 1/3 of the particles are going along the y-axis, and 1/3 of the particles are going along the z-axis. Or you can say at any particular instant, 1/3 of the push from all the particles is along the x-axis. 1/3 of the push is along the y-axis, and 1/3 of the push is along the z-axis. You can also look at it that way without separating the particles, saying for all the particles, they have components. Here they go more with components, I think. So you got this right here. MVX, he's coming right at it. And then the thing comes right back. It's like a baseball being hit. Let's talk about this. In other words, you can say that going this way is positive. When he hits, he goes negative. So, as far as components concerned, they do it more with components. I'm kind of throwing a fastball by you in a sense. If you all use the baseball terminology, I'm kind of throwing one by you a little bit. You can do this with components, it works just fine, or you can do it, like I said, separating all the molecules completely and say, all right, only 1/3 of them are doing this, 1/3 of them are doing that. I'm saying, they can do a lot of stuff like that. Or you can say 1/3 of the components go this way, 1/3 this way, 1/3 that way. That's more realistic, actually. Same conclusion gets drawn though. If the component here hits with that kind of momentum, and then comes back with the same magnitude momentum, but in another direction, we got this. Sounds good. That's one particle. That's what one particle's component of X did. On average, it'll do this against another 4 walls. It'll be these 2 walls. See this happen. Let's be careful. How many walls are in this cube? 1, 2, 3, 4, 5, 6. Every wall is going to have this happen to it. What does that mean? Well, those that have calculus, they do it a little more subtly. They do it with a differential, with differential elements, okay, with using derivatives, but that's not a big deal. It's not really a big deal right now. So for any of us, it's not a big deal. What we got is, it true that change in momentum over change in time is force? Yeah, sure is. This is just one particle now. or the component of one particle. Now notice that same particle's got components elsewhere. He's got components in the y direction, and he's got components in the z direction too. So that particle, when he's making all these hits, he's also going to hit the other walls too. Yeah, that's fine. We'll account for all that. Well, 1/3 of the time he's doing this. The other third of the time he's doing it in the y direction. The other third of the time he's doing, so 1/3 of the time he's in the x direction, 1/3 of the time he's in the y direction, and 1/3 of the time he's in the z direction. I gotta ask you a couple questions. This is just one particle, particle 1. We got this. Sounds good to me. Now it gets interesting. A lot you can say. Now it can get really interesting. What's delta T? I got a question to ask you. If I drive to Chicago at 50 miles per hour, and Chicago's 100 miles away, what's 100 miles divided by 50 miles per hour? What's 100 miles? What's 100 miles distance? What's 100 mile distance, D? What's 100 mile distance divided by 50 miles per hour? 100 divided by 50 is 2, that's 2 hours. Are you telling me that yeah, I'm exactly telling you that. In fact, let's talk about it a little bit. I know that D, huh? Yeah. We said it's a cube. And I said, man, this thing could be shaped like a rock and I can make it work. It'd be long-winded, and I want to be talking to you guys face to face in person, but I know we can make it work. Just know it's possible. Know that it's possible and know that it works. For now, we'll just stick with the easy stuff. And we know the hard stuff works. We know it. We can prove it. D over delta T is D sub x. Multiply by delta T on each side and divide by that. That's crazy. What are we talking about here? F1, so we're just staying with the component. I'm just saying, man, okay, great. There is a component here. On average, it's going to be, and this is weird, forgive me guys, I don't want to beat this to death or anything, but the Vx component can go anywhere from 0 to being straight out as big as the actual velocity. You just go straight out and hits it. But on average, about 1/3 of the time it's going to hit with a component that's going to be whatever size that is. We'll have to cross that bridge. We'll get to that in a little bit. But it's going to have an average size on average over the long term, how it hits in the x direction. It's that same average size when it hits in the y direction, statistically speaking. And it's that same average size when it hits in the z direction, statistically speaking. So let's see what we have here, guys. We said this, and here goes. Let's see that. Start playing the games, guys. Start playing the mathematics. We gotta play it. F1 is, that flips over. Forgive me. One mistake. Let me come right back. That's all right. It's okay to be wrong if you can just catch it on occasion. The D is off. Why is the D off? I want to know the time between collisions. If this guy collides right here, let's just say a collision happened right here. Collision happened against the wall right here. And he's going to collide again against this wall right here. The distance is D between them. Right when he collides, a collision happened. When is he going to collide again? He's going to go, when is he going to collide again? He started here, he collided, right after the collision, bam, you hit the stopwatch. Right after the collision, you hit the stopwatch. So he hit once. Okay, done, he hit. Right when he leaves, I'm not worried about it. He hit once, he leaves. I hit the stopwatch right after he hit. He leaves. He leaves, he goes D, and then does D again to come back. He travels 2D to come back, guys. He travels across and back for the collision. We're talking about one wall right now. You're going to say to me, yeah, what are you talking about, Bayless? He hits here, he goes D, he hits again. He only went D to hit again. True, we got to talk about that. He went here to here, and he hit somewhere else. He went from here to here, and he hit somewhere else. He bounced and hit again here. I only care about one wall at a time. I only care about one wall at a time. If you don't want to care about one wall at a time, then we got to figure something else out. Then we can still do it, but it's not the time frame under consideration there. The number of hits aren't going to be as many. I mean, when we're talking about, there's other mathematics. There's a little bit other mathematics we have to do. Very, very much something we can take care of. But if that was the case, you've got to look at what's happening one wall at a time. Why? Because when I figure out the pressure, ladies and gentlemen, and by the way, what is pressure? Pressure is force divided by area. We'll cross that bridge a little bit. Force divided by area. But when I want to figure out the pressure, I want to know how much force hits an area. Well, here's an area. I want to know one wall at a time. If I find it out for one wall, I'm done. Because it's doing the exact same thing for the other 5 walls. There's 6 walls on this thing. So we're doing something like that, you guys. So you got this, so it's 2D. So my fault on that. Forgive me. Divided by dt. The total distance traveled is 2d. 2d divided by vx will give me the delta t I want. Here it goes. Forgive me here. Okay, right. Over D, right? Yeah. All right, guys. This again, you're doing this one wall at a time. I'm not trying to figure out the pressure. Hey, I want to know the pressure here and the pressure there. If everything's happening identical to all 6 walls, do it one wall at a time. Then find out the time period that transpires between collisions for the same wall going one wall at a time. That's important. That's where I made the mistake here, and that's why I corrected it. Okay, so here it is. So you got this. Well, good. I'll tell you what I'm going to do. I want to know the force on that wall. Why do I want to do that? Okay, forgive me guys, forgive the repetitiveness on this thing, but as my Russian teacher taught me, повторение мать учения. Repetition is the mother of learning sometimes. So, what's going on here? I'm talking about one wall. Yeah, I know, it's identical to all the other 5 walls. All 6 walls are identical. If I find one wall, I'm going to find the pressure. Why don't you find the total force going on? Total force. Okay, I got an idea. Total force. Why don't you add all these up? Why don't you add all these guys up? This is V1x. This right here is V1. If you really want to know the truth, this guy's V at this point for this F1, in general, F is equal to mvx squared over d. For just one of them is this. For molecule number 1, I painted him number 1. Let's paint another molecule, we'll call it molecule number 2. Okay, put a 2 here, put a 2 there. Let's sum all of these and we're set. Let's sum. Now every one of those little particles, no matter what number is attached to them, has got the same mass. And the distance they travel is 2d, and I did all the mass, and the 2's cancel, so d don't change either. V sub I x squared. What does that mean? That means that m over d doesn't change. But these guys are getting added up. V1x squared. V2 x squared. V3 x squared. Plus dot dot dot. Got all this written down, guys. Didn't quite write that notation in the notes, but and I went down to here. It's very similar to that what I have. Very similar to what I have in the notes. So we did it. This is for many molecules, as I said. Okay. Now it gets interesting. Let me try to make the move the right way. I mean, so we don't have an issue here. All right. I'll tell you what. You tell me how you feel about this. Trying to think how I want to talk about this, guys. I'm going to do something here. I write it a little differently in the notes, but I'm going to talk to you guys. You're going to help me out here with this whole thing. I still want to leave that up there. I know that if I go back and I got to write it again, everybody, I'm gonna want to throw my head against the wall, I guess, right? So let me leave it for a while. Let me see if I got to change it. So let's see. I got to talk to you guys. I'll tell you what I'm going to do. I'm going to add all these square velocities together. Okay, yeah, big deal. So what? Yeah, I know. There's N. There's a total of capital N. Capital N is the absolute total. And that's right here, guys. Capital N is the total of all the molecules present. And about 1/3 of them go this way, about 1/3 go that way, about 1/3 go the other way. Yeah, I can do that. Or I can leave all of them and go with the components. I chose to go with the components. I said, I don't know, man, the way this is going on, if this goes on long enough, on average, the x components of all n molecules, each one of the n molecules on average has as much x component hitting the 2 walls associated with the x-axis. They have as much x component of velocity hitting the 2 walls associated with the x-axis as is occurring with collisions with that same one molecule hitting along the y-axis, hitting along the z-axis. Same amount on each one, I'm saying. On average, whatever the heck that is. I got a question to ask you. I'm going to say the average of the squares of all the x components is equal to v1x, v2x squared plus dot, 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 plus sounds good to me. I'm averaging all the squares. Interesting. Okay. This is the square. This is the average of all the squares. I'm averaging all the squares. Wait a minute. What happens there? If you multiply by capital N, if you take capital N, the total number of molecules present, if you take capital N and multiply it by the average, of v sub x squared, that's going to give you v1x squared, v2x squared, plus dot, dot, dot. Sounds good to me. This is just F1. This is everybody. This is everybody. Well, wait a minute. That right there is equal to this. M over D times this. What's that? What's this? Looks good to me so far. Okay. This is very important. We all follow from one another, guys, if we're careful. If we're careful. Fascinating. Well, let me write it. I'm not sure it matters much how they write it, but let me just write a little bit. Let me write it the way I wrote it in my notes. It's not a big deal. We're not going to make a big deal out of it, but you got this guy right here. It's the average. It's not the average of the v squared. It's the average of the square of v. Not the average of the v squared. It's the average of the square of v. All right. That's why I wrote in the notes. And there's some conclusions we're going to draw. Having said this, erase a lot of that over there, because we can always come back and get it. Let me erase it and go over there and write some stuff as well. So I'll be walking around a little bit. Remember this thing way over there, guys. I'm going to come back and tinker with it a little bit. Let's see what we can say. Okay. So this is interesting. Usually I'm the only guy who says it's interesting. I get that, but I mean, all right, so let's look at this, guys. Can I talk to you about something? Man, that Pythagorean theorem, those ancient guys were talking about, man, who knew that it was going to have applications in all kinds of physics. Einstein used the Pythagorean Theorem when he did his theory of relativity. Pythagorean Theorem gets used in electrical engineering. It gets used in complex analysis and mathematics. It gets used in a lot of places, you guys. Tell me what we're going to do. This is a more elaborate form of the Pythagorean Theorem in three-dimensional space, but it's absolutely valid. On average, the average of the square velocity of any particular item is the average of the v sub x squared plus the average of the v sub y squared plus the average of the v sub z squared. Because the motion is random, you guys. Because the motion is random. I was telling you this earlier. The average of the squares, regardless of direction, on average is equal. I'm not saying at one instant for one particle. I'm saying for any one particle over a long period of time, there's the average amount of component going in the x direction, the average going in the y direction, and the average going in the z direction are all equal to each other. What does that mean? It's believable. It's believable. There's some, even if the thing is shaped like a rock, believe it or not, volume is volume. If I figure out a volume in the x direction, integrating, if I'm using calculus, integrating going in the x direction, or integrating going in the y direction, or integrating going in the, integrating going in the x direction, or integrating going in the y direction, or integrating going in the z direction. I want to write it like that. It's the same volume I'm getting. The mathematics holds. It's beautiful stuff. Rather elaborate how we got to do it, but if they're all about equal, on average, if they're all about equal, this is about a third as big. That means each one of them is about a third as big as that one. Each one of these, the average of the square of v sub x, plus the average of the square of v sub y, plus the average of the square of v sub z, each one of them is equal, long duration, equal, taken in aggregate, equal amount. If it's equal amount, this is 1/3 as big as that. That's also 1/3 as big as that. That's also 1/3 as big as that. You write it like this. Again, chalk is out of this world. Maybe it's just me. I don't know. Try it again, guys. Yeah, you heard me deliver the speech. It's there. The same is going to hold for the Vy squared. The average of Vx squared is 1/3 the average of the total V squared. Etc., etc. The average of the v sub x squared, the average of the square of v sub x, the average of the square of v sub x is the average of the square of v. Same exact conclusion. These are all equal. So the v sub y, the average of the v sub y squared equals the average of the v sub z squared equals the average of v sub x squared. So it's going to be equal to that. So we did some stuff. We said, it's a lot you can say here. I mean, we said, now we're dealing with one wall. Yeah, I know, but I told you every single wall gets hit the same way. If every single wall gets hit the same way, I can find the pressure just by finding out the pressure on one wall, because every other wall gets hit the same way. Every other wall gets hit the same way. So if I can find it for one wall, I found it for all the walls. And I found it for the pressure of the gas in that container. That's very important. Well, there we go. Let's go speed it up a little bit here, guys, if I can. I got this. I set all that way over there to the far right-hand side. And we've had it. We got it. Anyway, it's the far lower right-hand side. What do I do? Well, I'm going to write it again. I mean, I got it here. This is what I just wrote. Sounds good to me. What did we say this guy was? We said this guy was that. Is what we said. So if that's the case, that's a third of that. All right, so what do you got? You got F. Forgive me here. Just rewrite it. Put 1/3 the average of V squared. And that comes, put that guy here. Put a 3 right there. Interesting. It's not the square of the average, it's the average of the square. It is not the square of the average, it's the average of the square. Interesting. A lot going on there. It's almost like we just broke up the n particles into 1/3 of the particles going in the x direction, the other third of the particles going in the y direction, and the other third of the particles going in the z direction. It's pretty beautiful. It almost looks that way. Let's talk. Isn't pressure equal to force divided by area? Isn't pressure equal to force divided by area? Isn't force for that one wall divided by area? It's the area of the wall. Hey, isn't this a cube? I said I could do this if the thing was shaped like a rock. I could do this if the thing was shaped like a rock. It wouldn't be easy, but I can prove that it's true. It takes longer than we have, but we can do it. Right now, we're not, as we said, we're not even worried about that right now, but remember that it's true. We can prove that it's a rock. Shaped like a rock, I can still prove it. You can prove it too. We can all prove it. All right, this is D, that's D. D times D is the area. That's a square. D by, it's D right here. D right here. D times D is D squared. All right. Pressure equals, force divided by area. Got that. I mean, that's superfluous. I mean, that's that. That's what that is. That was that. So this guy, as we do it, let's write a bunch of ways here. Let's write the 1/3 here. Let's take the 1/3 out. We got the n over, okay, now, careful. D squared on the bottom, D squared on the bottom here, you can bring it up. You're not flipping anything. It's not 1 over D squared where you would flip it. It's just D squared on the bottom, you bring it up here. D times D squared is D to the 3rd. So what we got here is, here's n. I took the 3rd out of there. There's an m average V squared. We got that. Over D cubed. Yeah, I got another question to ask you. There's a d squared on the bottom, ladies and gentlemen. There's a d squared, a d cubed on the bottom. You gotta access this stuff. I'm so used to in person with people, I like to leave stuff up there a bit. But you guys got the film, you come back on it. There's still no substitute to seeing you guys in person, though, I'll tell you that. So hopefully that happens soon for us. Okay, so what's going on here? I left that up there, the way corner right here. Left it up there, it's got significance. Okay, this bottom thing over there, what's that all about? We wrote it, what's d cubed? I mean, I asked him, this d cubed right here, here's d, and here's d. D times d, length, take a look. Length times width times height is volume. D times d times d is volume. That's volume. What happened? Well, it's volume, it's volume. I mean, you got P is 1/3. Try to see here what I want to say. I don't want to say it. N over V. V is big V now, volume, right? It's volume. 1/3 N over V. What I did was, guys, here's 1/3, here's N, here's V, here's MV squared. The bar's right here. It's there, it's not visible. It's that. Pretty fascinating stuff. Tell you what. So what I'm going to do? Let me put a 1/2 right here. Why the heck did I put a 1/2 right there? I got to do something now that I did it. I put a 1/2 right there. I made it half as big. I made the problem half as big. That's okay. After I make it half as big, I'll double it. The pressure is proportional to the number of molecules per unit volume and to the average translational kinetic energy of a molecule. What does that mean? It means this. It's inversely proportional to volume. If it's a small volume, but a lot of molecules, and all of them have a lot of kinetic energy on average, a lot of kinetic energy and a lot of molecules for a given volume is a great amount of pressure. If you make the volume half as big, but you keep the same number of particles and the same amount of average translational kinetic energy per molecule, this is average translational kinetic energy per molecule. The average translational kinetic energy per molecule, if it's big, and if the number of them is big, and you make V real small, of course pressure is going to be huge. Already it's looking like this, because T comes from average translational kinetic energy. The pressure is proportional to the number of molecules per unit volume. The pressure is proportional to the number of molecules per unit volume and to the average translational kinetic energy of a molecule. Essentially what they're saying is here, guys, they make it work. So keep that in mind, it's important. Bear with me. There's a reason this stuff doesn't get proved a lot sometimes, right? Or the reason is, oh, we'll get it, we're on pace. We're on pace to do everything we got to do. And if not, this is so important I have to do it. You know what I mean? The other stuff, not as much. You guys are going to be fine. So let's talk. What just happened here? Well, yeah, I'll let you know what happened. I mean, what happened is we are just going to kind of like make this make sense. I mean, we are going to take this bottom guy, he's got an N in there, and we'll figure out how they like to talk. Basically, this is pointing to that reality over there. And this reality over here, you guys, and over there, this thing's empirically proven, can be empirically proved, and at the microscopic level, it makes sense that you can empirically prove it. That's a big thing to look at when we're looking at this thing. All right, let's talk. Okay. Well, I guess PV is PV. They better be equal. Yeah, you know, they are. Don't worry. I mean, I don't want any of us to worry about this guy. They are equal, and it makes sense they're equal. You know, there's these two guys right here resemble this. That's a constant. That's variable. This is a constant. That's variable. This is a constant, that's the also. N's are here in both places. That's a constant, that's a constant. These guys are only going to be off by a little bit. The bigger the temperature, the bigger the average kinetic energy of an average molecule. The average kinetic energy per molecule is directly proportional to the temperature, and man, look at it. You can see that it is. You can see that it is. Without too much imagination, we can see that that's true. Let's set them equal to each other. PV equals PV, let's go. Here it goes. There's a big N on each one of these. Here goes nothing. Set them equal to each other. Yeah, okay. How about you divide by capital N on each side? How about you divide by KB? Forgive me. Yeah, go ahead. Divide by KB. Temperature is going to be, see exactly, they left some stuff in here. That's okay. We're gonna play their game that way. We're gonna divide by KB. 2/3 kb, 2 over 3 kb. 2 over 3 kb. Divide by kb, and you got the 1/2 right here. Look, I'll spell it out in no uncertain terms. The average kinetic energy per molecule is equal to the temperature if you multiply by that constant. 2 is a constant, 3 is a constant, k sub b is a constant. Absolute value temperature is directly proportional to the average kinetic energy. That's crazy. They did a whole bunch of stuff. They said the KE total, if you average everybody together, so we got this, KE total, that's everybody, all M particles. Let's add them all together. Fine. let's take the average kinetic energy per particle. The particle is only of mass m. It's not a lot of mass. Yeah, it's one particle. The total, once you multiply it by n particles. N particles, huh? That's KE total, huh? Yeah, sure is. What did we say here? We got this, N right here. Try to see here where I had it. Right, and right here. So if you were to leave it, I'm trying to think here. Okay, I want to do the math right for you guys. Let's come back to here. NKBT is 2/3 n times this. Okay, hold on. Here we go. What I told you not to do, I just did. Okay, it's the average of the squares. So here's the squares, the average of the squares, not the square of the average. Here we go. N times 1/2, N times 1/2 M average of the squares, N times 1/2 M average of the squares. That's him. All right, yeah, right. That's him. That's KE. Yeah, I know. There's a 3/2. There's a 2/3 here. I gotta get this. I want this to get the KE total. I want this. What would you do here? What would I do here? Since they're equal, that's what it was before. How about you multiply by 3/2 on each side? So this happens. 3/2 N KBT is equal to this. Capital N, KBT. Wait a minute. Isn't capital N, KBT equal to PV? Yeah, and PV is also equal to nRT. So this and this are equal to each other. So put the nRT in place of that too. Here it is. Wow, looks similar to what we had, man. That's where it's coming from. Of interest, for a monatomic gas, translational kinetic energy is the only type of energy the molecules can have. Say it again. Of interest, for a monatomic gas, translational kinetic energy is the only type of energy the molecules can have. For diatomic and polyatomic molecules, additional possibilities for energy storage are available in the vibration and rotation of the molecule. So that's why you see them later on, you see they put little different numbers other than 3/2 in front for those. That's crazy stuff. They do a lot of stuff here, guys. I mean, this right here, wow. What is this? What's nRT? What's nRT? It's PV. This is also PV. Wait a minute. If they're both PV, if they're both the same thing, and they pertain to that, so that's the pressure, huh? Kinetic energy, right? And we got that. So if you wanted to find the pressure, we already did the pressure. We had this. Yeah. Forgive me, guys. It's coming right back here. This is so huge, I forgot it. Or I walked over it, passed over it, whatever I did. You know we got to here. Pretty fascinating stuff. I mean, how that all plays out. We found PV, and then we said, okay, go with that. If if, go with this. Go with this if you want. If you don't want to go with this, capital N, KBT, go with the other one. Go with PV equals nRT. PV equals nRT or this one. We already said they were equal based on the games we were playing. We said that if we do the experimentation correct, if we do the experimentation, ladies and gentlemen, correctly, if we do the experimentation correctly, ladies and gentlemen, we find this to be true. Great. Now let's talk. Well, let me write it another way. Now let me go and try to look at these two and see what I can say. PV is equal to that guy? Fine. If you don't want to make them equal to nRT. PV is nRT and put an nRT in here. If you put an nRT right here and you tinker with this thing, I can still solve for kinetic energy and make it proportional to this. So there's a lot going on here, guys. There's a lot happening. Let's talk. I mean, we were tinkering with this stuff a bit. We did a lot of stuff here, guys. We found, we found out the conclusion earlier. We said that's KE total. Can you actually find out the velocity then? Yeah, that's KE total, right? KE total, let's not, this is the total for n particles. Let's try that again. This is the total for all n, this is the total for all n particles. Great. This is the total for all n particles. Divide by big N. Divide by big N on each side, and then you'll find the average kinetic energy for one molecule. Oh, divide by big N, if I do that, I got this. Here we go. I divided by big N on each side, so I'm here. We already said a lot of this stuff. What do you say you multiply by 2 and divide by M? The mass of one molecule. Square root each side. That's interesting. This guy, square rooted, they call it VRMS. That's the root mean. It's kind of like an average, but it's the square root of the average of the squares. So they call it the root of the mean of the squares. The root of the mean of the squares, and that's equal to this, and that's equal to okay. Let me write that another way. So it just becomes this guy. It's V RMS. It's a kind of average. It's the root of the mean of the squares. So they call it the root mean square. Yeah, absolutely. Another way to write it? Kind of looking, I guess. Sure. KBT, right? And if you take, try to think here, 3 KBT, 3 here, 3 nRT equals 3 NK. Divide by big N on each side. Divide by big N on each side. And you got a capital RT, the 3 capital RT. The 3's there, that's fine. Multiply by 2, 3 KBT, square root of that over M. What you're gonna get is, actually, you come right here, guys. You get the KBT, forgive me here, the KBT would be, the 3/2 are there, the n is gone, so it's small n over big N. That'd be the KBT. Small n over big N divided by small n. So small n, so it's RT. I'm just taking that. I tinker with this, and I can do the mathematics to get it there. Divide by n times small n. N times small m. All the small particles. What are all the small particles? Each small particle multiplied by the number of particles. The mass of one particle multiplied by the number of all the particles. All the particles times the mass of one particle is the total mass. It's capital M. And that's just the mass that's there. The mass of all the gas that's present there. Of all the aggregate of what's there. That's it. There's a 3 here, I'm sorry. The KBT and the nRT are equal to each other. If you look at it. Cancel 3/2, cancel 3/2. Divide by big N, then it's just KBT is N over big N RT. So yeah, the 3 that was always present, you can always leave it. So anyway, guys, I'm sorry, I'm kind of all over the place with this thing, but it is important. It's pretty, hey, what's going on here? What's the speed of this thing? What's the speed of the average molecule? My common sense tells me if it's really massive, it doesn't have to be going that fast to have a lot of kinetic energy. A train going at 5 miles per hour has more kinetic energy than that race car going 200 miles per hour. Very likely, just by virtue of the mass that's present. So that's some interesting stuff there. Again, the thing to emphasize that we didn't directly do a numeric derivation. We did not do a direct derivation. Hey, that and that, they're equal. No, but we worked under the assumption that we can do an experiment, a lot of experiments, and that's true. If that's true, let me tinker with the constants, and that is also absolutely true. If I tinker with the constants, I built this stuff based on the constants. I can prove this. If I do enough experiments for a broad range of circumstances, this can be proved. Then we can just play with the constants, and this follows directly. And then we do some of the other stuff we did, and wow, the connection is very obvious. Okay. Am I going to ask you to do this on any exam to prove it like this? No. Am I going to ask you to do this on a final exam? No. But it's good for your personal enrichment kids to look at some of this stuff. All right. That'll be it for thermal processes, that'll be it. Thank you.